Find missing trigonometric ratio based on the relations without relying on these trigonometric identities. Let's do a recap on the first method which we used previously. We saw how to calculate the sine if we have the cosine by using the Pythagoras theorem in trigonometry. Also here it says that theta is reflexive and it was in the third quadrant. Thus we obtained the exact value and sign of the sine. Also tan is sine over cosine and we substituted the values in order to get the tan. Now let's apply the second method. We will work on the basic definitions of the trigonometric ratios. So, sine is opposite over hypotenuse inside a right triangle. And tan theta is opposite over adjacent. So we have a right triangle which represents angle theta in a specific way where we can calculate these sides. Remember that theta is reflexive, so that means it is either in the third or the fourth quadrant. And since the cosine is negative, then it cannot be in the fourth quadrant because here the cosine is positive. So theta is in the third quadrant. This is angle theta. When we want to work inside a right triangle, we need an acute angle, not a reflexive one. That is why we need to build the acute angle which we will need to compare with the theta. We will continue this side like this and we will name this angle phi. It is this angle here. So, theta is phi plus 180 degrees. This is the relation between the reflexive angle and the acute angle. So phi is an acute angle. Okay. We want sine theta. We know the sine theta is in the third quadrant, so it is negative. So here we have minus sine phi. While tan theta is positive, so here we have plus tan phi. Thus we defined angle phi and we will draw it inside the right triangle as an acute angle. This is the right triangle and here we have angle phi. Pay attention that cosine theta will be represented as cosine phi, which equals the positive value of 3 over 5. Cosine phi is 3 over 5, so the adjacent is 3 and the hypotenuse is 5 because cosine is adjacent over hypotenuse. Now look at this side here. We will name it x. To get the remaining values, we need to calculate the value of x. So, by using the Pythagoras theorem, hypotenuse squared is 5 squared equals to the first side, which is 3 squared plus x squared. 25 equals 9 plus x squared. X squared is equal to 16. Of course, x is positive square root of 16, which is 4. So x here is equal to 4. Now for the sine phi, it is opposite over the hypotenuse inside this right triangle. Opposite is x, so 4 over the hypotenuse, which is 5. So we have 4 over 5. Since we calculated sine phi, we know that sine theta is minus sine phi. Thus, sine theta is minus 4 over 5. Now, for tan phi. It is opposite over adjacent. The opposite is 4 and the adjacent is 3. So, 4 over 3. We know that tan theta is plus tan phi. So it is the same value, which is plus 4 over 3. Look at the description. Use the right angle triangle with the acute angle phi, where cosine phi equals 3 over 5 and angle theta is 180 plus phi. Use Pythagoras theorem to find the missing side x, which is 4. Thus, we were able to calculate the sine phi and tan phi, which allowed us to obtain sine theta and tan theta, due to the relation of the theta and phi. Look at the hint. Given an angle theta of any size, you can always work with its related acute angle phi. So, whatever the size of the main theta angle, in this case it was reflex, so more than 180, you can still find a relation with an acute angle just like we did here. Use a right angle triangle, work to find sine phi, cosine phi, and tan phi. Phi is the acute angle which has a relation with theta. However, remember to consider the quadrant that theta is in when giving sine theta, cosine theta, and tan theta. Thus, we need to always remember in which quadrant we are working, and we need to connect the trigonometric ratios of angle theta with the trigonometric ratios of angle phi. Now we have finished the second method. We did not use the trigonometric identities, but we used the concepts of right angle triangle and the initial definitions of the trigonometric ratios.